guys, and welcome to another video. In this video we're going to be taking on this generalized integral right here. It's not a super interesting integral, and we've done a similar one in the past, but I think it's a really cool formula just to see, and if anyone needs to have a formula for solving this integral, then here's a solution for it right now. So let's go ahead and jump into it. So the first thing we need to do is rewrite this in its exponential form for sine, and then we'll separate all the natural logarithms using the multiplicative properties of the input of the natural logarithm. We can ignore these two terms right here because they are completely imaginary, and we know that our answer overall is going to be completely real. So essentially what I do in these types of problems is I'll just ignore everything that's imaginary, and then I'll take the real part of the rest of the answer as well. And then, so we're left with this negative ln2 times x to the n term, which is easily integrated, and this x to the n times natural log of 1 minus e to the negative 2ix dx. Just so you know how I got this term, basically what I did was I had e to the ix minus e to the negative ix, and then I separated this into e to the ix times 1 minus e to the negative 2ix, and I separated the natural logarithms. So this first term is easily evaluated, and of course we need the real part as well, but I'm just going to ignore this and then get rid of the imaginary terms at the end. So we're going to use this identity that the natural log of 1 minus x is negative the sum from k equals 1 to infinity of x to the k over k. So this gives us this summation right, or this integration right here, this integral right here with a summation as well, just taking this as this x. And now we end up with this kind of difficult to do integral, but luckily there is a simple way to turn this into a generalized formula using integration by parts. So if we repeatedly differentiate x to the x and x to the n and integrate e to the ax, we're going to end up getting this pattern right here. And we can summarize these terms by n choose m times m factorial times x to the n minus m, and we also have e to the ax over a to the m. And we're just going to get a bunch of these terms, and we're going to add up these terms diagonally and alternating in sign. So x to the n is going to go to the e to the x over a, and so on and so forth. And this series will terminate after the last term when m equals n. That's going to be a constant term in the d column, and then once we differentiate that, that'll be a 0. So that's going to look like this. Just a summation, just using these arrows to show which term gets multiplied by which term. So this is our summation, and in this case, a is actually going to be negative 2ki, so we can go ahead and plug that in. So we get this expression right here. First, our other integration right here, and then this infinite summation, and then a finite summation on the inside. And this looks like it could get really hairy really quick because we have an infinite and finite summation together, but luckily the infinite summation we're actually going to be able to bring inside and evaluate rather easily. And then we have this expression, x to the n minus m and e to the negative 2kix, evaluated at pi and 2 at 0. So at 0, all these terms are going to disappear, except for the term when m equals n, because then this is going to be x to the 0, so when we evaluate it at 0, it will have a value. So you'll see I added this in right here in green. This term, when m equals 0, x to the n minus m evaluated at x equals 0 doesn't disappear. However, notice that on the bottom, since we have this m plus 1 right here, we're actually going to end up getting an I in the bottom, and this is going to end up being completely imaginary. So we can actually ignore this last term, even though it does also show up, which is kind of an anomaly here. So for the rest of them, we can just assume that this term, when we're evaluating at x equals 0, goes to 0, and we can only look at the pi over 2 term. So I've gone ahead and plugged that in right here. Notice that e to the negative 2kix when x equals pi over 2 is just e to the negative ki pi, which is the same as negative 1 to the k. Then we can go ahead and expand this into the negative 1 to the m plus 1, k to the m plus 1, I to the m plus 1, and 2 to the m plus 1. Then we can cancel the negative 1 to the m on both sides, or on the top and bottom, sorry. And then we're going to get minus ln 2 pi over 2 to the n plus 1 over n plus 1, plus the sum from m equals 0 to the n of n choose m factorial over I to the m plus 1, 2 to the m plus 1, pi over 2 to the n minus m, and then bringing this k summation inside, we have 1 over k, 1 over k to the m plus 1, and we have negative 1 to the k, and combining all these together, we get this summation right here, which just ends up being negative eta of m plus 2. So once we do that, now notice another thing right here is we have this I to the m plus 1, and as we said before, we can just go ahead and ignore all the imaginary terms. So when m is an odd number, this will be part of the reals, which is exactly what we want, but when m is even, this won't be real, and so we have to ignore those terms. So we're going to do a little bit of a transformation. We're going to replace m with 2m plus 1 and 2m plus 1 and then change the bounds, and this is going to let us select only the odd values of m. So notice I changed the bound right here, and you can plug in any value of m, and you'll find that when you plug in m equals this upper bound, it's going to be the smallest or the largest odd number less than or equal to n. So that's going to give us all the odds, and then I just went ahead and plugged in 2m plus 1 everywhere. This term right here becomes negative 1 to the m plus 1, and so finally, once we reorganize everything, we get our final expression, which is minus ln 2 pi over 2 to the n plus 1 over n plus 1, plus the sum from m equals 0 to the ceiling of n over 2 minus 1. And our summand is negative 1 to the m, n choose 2m plus 1, 2m plus 1 factorial over 4 to the m plus 1 times pi over 2 to the n minus 2m minus 1 times eta of 2m plus 3. That is quite a mouthful, but this is our overall expression for this pretty nice integral, and I think it's a pretty nice formula, though it's not very fun to deal with. Anyway, I hope you guys enjoyed the video, and I'll see you next time. Thanks for watching.